All right, let's continue working with our circuit simulator to practice for week 11, completing our A10 assignment. So this is the circuit we'll be working on, but before we do that, let's quickly revisit our goal here. We want to complete the virtual circuit modeling experience, develop an understanding of resistive circuits, discuss some of the concepts of Ohm's law, Kirchhoff's voltage and current laws, and then capture some data similar to what we'll be doing in studio with the meters and real circuits. So let's take a look at our, you'll have the spreadsheet open. Let me delete some of the data I had here so we can add it in. All right, we'll have the sheet 2, the series circuits sheet from your spreadsheet open, and then our circuit simulator. Let's go ahead and open up our previous file that we saved so we can add to it. So we'll open a file, and I've got it going to my location where I've saved it. I'm going to open that, and that allows us to restore what we had. I'm going to move it off to the side here, zoom out just a little bit to make some room. Zooming, and I'm clicking and holding that scroll wheel to move things around. Another way to get started on this is to center the circuit, but since it came in centered, now we can zoom out and click it to the right. Okay, so we'll zoom in a little bit. All right, so we need to add some elements. Let's take a look at that image again. Our circuit that we're going to replicate in the real world is this piece. So it is a series circuit of 3 resistors. We've got our Uno providing power, our LED lamp and switch, so we can check to make sure power is coming to the breadboard. There will be that video to watch so that you understand how the breadboards make connections. So we've got wires simulating our connection to our first resistor, through our first resistor to the next wire that couples to the next resistor, and so on to the third one, and then finally it returns back to the negative or ground side of the power supply. So positive being red, negative being ground, and our circuit. But now let's see what we can do about creating this. This format allows us to take the measurements easily in class. So let's do the same thing in our circuit simulator. So let's add a resistor. So I'm going to select that one that we've already got because it's the same. Copy it, paste it. I'm going to move it around a little bit. Oops. Okay, and then copy it and paste it again. Give it a little bit of separation there and paste it one more time to get us our circuits. Let's add some wires. So our first wire to bring our negative side of our power supply down and then connect it temporarily to the end. Let's add in some extra wires to close these circuits. We won't connect them now, but we'll put them in there. Extra wires to close the circuits. And some wires for taking voltage measurements. I'm going to add them right here. And the last one there. All right, so now we have that. Now we need our meters that we're going to take measurements with. So we'll go to Draw, Outputs and Labels, and we're going to take a voltmeter or scope probe. And I want to place one of those right here. 0 volts, so that gives us a clear sign that's a voltmeter. Let's do the same thing for the outputs and labels, and then ammeter. So I'm going to put that above one of these sections here because it'll be replacing the wires. So hit the space bar, just move things down just to line it up a little bit. So you can see that that matches up with our intended circuit. It's a 1, 2, 3 resistor series circuit. We'll set up one circuit at a time, take our measurements, add in the next resistor, repeat those measurements, and add in the final resistor, and repeat those measurements. All right, so let's go ahead and get started on that. Let's close the first resistor into our series circuit. So I'm selected the last wire, take the end of that, and connect it to the first resistor. I'm also going to take the extra wire and close the circuit. So if you're observing the current speed here, you'll see voltage. The voltage from the power supply is pushing current through the circuit. So it's going through the resistor, but also out through the LED. And for now, we don't want to take a look at this. I'm just going to uncheck that switch so that now the current only goes through the circuit in one direction. Now, of course, we can hover over these objects in this environment, reading the voltage current in the lower right portion of this window. You can hover over the single resistor. But what I want to model this week is how we're going to take those measurements in a practical sense in the lab. So in order to do that, measuring the current, we're going to pull this wire out. When you're using meters, you have to break the circuit. So we broke the circuit, and we're going to add the meter in. Excuse me. Click on it once, then go select it and move it in. And you see it's busily measuring the current passing through it. It completes the circuit itself and then also measures that current. And our meters will do the same. Let's do the same thing with the voltage. This voltmeter, I'm going to slide it down and connect it to the top of the resistor. And this is the way voltage is measured across an active circuit. With some caution, but for low voltage things like we're doing, very simple to do and reliable measurement. So let's collect some of this data. So we've got voltage from the voltage source. We know we assigned it to 3.3 volts. And according to our hover meter here, it's providing 3.367 milliamps and a power of minus 11.112 milliwatts. So let's go ahead and enter that data in our circuit here. So we've got 3.3 and 3.367 milliamps. And let's go ahead and use the power equation from last week. So I'm going to switch gears here, go revisit. Electric power from last week while we were pump testing was the voltage times the current, and that's still true here. So let's go use that in our simulator. So the green ones are calculated values. So we're going to do voltage times current. And because the current is in milliamps, the answer is going to be in milliwatts. And so this 11.11 here, I'm going to reduce the number of decimal places here. Oops, click on that cell. So that should line up with our virtual model as I hover over the power supply, 11.11. And then let's take the data here. So we're measuring the voltage across the resistance at 3.3, and the current going through the resistor is also 3.367. Now these are ideal circuits, so the numbers will match very closely, but let's go ahead and enter that data. And repeat that power calculation. And then we also need to do the resistance calculations. Let's take a quick look at that. So in Ohm's law, through the reading, we found that the voltage in the resistive device is equal to the current going through the device times that resistance. So since we have the voltage and current readings, we can rearrange this formula to establish the resistance of the device equals the voltage across it divided by the current going through it. And so let's do that. So the voltage across the device here divided by the current going through it, 3.367. And this is, in order to get ohms though, we'll still need to also divide by 1,000 in order to get our resistance. Oops, sorry, multiply by 1,000. So we have 980 ohms. And because this is an ideal circuit that we're modeling, this value matches the value that we entered. So let's set up the second circuit and take some more measurements. So if we move the circuit to circuit number 2 and add in the wire to complete the circuit. So now we have a 2 resistor series circuit that's operating. And let's take a look at these measurements. The voltage source still supplying the 3.3. And if you look in the lower right there, now the current is lower, 1.684. And so let's go enter that. So 3.3, 1.684. Okay, and then let's check the values for the resistors. The value for resistor 1, voltage across it, 1.65. Current going through it, 1.684. So let's enter those. Check one more time, 1.65, 1.684. Okay, and let's go check resistor 2. So on resistor 2, I'm going to move the current meter over here closer to it. we'll see that it won't make any difference, but just to be clear, 1.685 across in voltage across the resistor, and then 1.68 volt 4 in terms of current milliamps going through the resistor. So let's record that data again. Okay, and we can copy these cells. And we can see that the power provided by the voltage source equals the sum of the power absorbed by each of the resistor, each of the components. So, and our last one, let's do that. Let's complete the entire 3 resistor series circuit. Close the circuit entirely. Pull the ammeter out and close the circuit, excuse me. Close the circuit here and here. And now we'll check the voltage across each of the devices. So we see that the voltage on resistor 1 is 1.1, the voltage on resistor 2 is 1.1, and the voltage on resistor 3 is 1.1. If we check the current before each one, 1.122. Again, you have to close the circuit. 1.122, and then not surprisingly, the current in the same wire heading toward the last one is 1.122. So let's record that data. Again, the voltage source is 3.3. The voltage is 1.1 on each. And then let's go back and check the current from the source, just to be clear. The current coming from the source is 1.122, which is the same for each of the data elements. So 1.122. And again, we can copy our cells down to do our power and resistance calculations. So again, looking at the power, the voltage source provides all the power, and the resistors divide that power up and absorb and turn it into heat, essentially. So let's take a look at this. So we've got our 4 resistor series circuit completed, and we're using the voltmeters and current meters, ammeters, to take those measurements. So once you've got it set up like this, let's do another save as command, and go ahead and click on that link to save it. And then again, I would want to rename that to match our So I've named it T-Pound A10 GU login. So put your team number in there and your GU login and put a -2 on it and save that file. We will, I'll go ahead and move that right now to where I want to save it. And we're good to go on that one. All right, so there's your measurements for the series circuits, and I will get ready here to add the parallel circuits.